All right, getting into chapter 4, getting into the wonderful world of trig. So a lot of this, at least to begin with, should be a refresher for you on some things that you would have Algebra 2 last year. So we're going to definitely want to reinforce some of those skills, and then we'll be expanding beyond. So starting out with some basic information on radians versus degrees. So we're all super familiar with the degree of an angle, and that's something we learn pretty early on in math, and we get sort of used to doing things in degrees. But we know another way of identifying angles within trig is oftentimes we'll use radians. And so just a reminder as what a radian is. If you were to take the central angle of a circle, it would have a measure of 1 radian if the intercepts of the arc with the same length as the radius of the circle. So in other words, let me just write this in. To get a measure of 1 radian for this angle instead of degrees is if you were to take, let's just say this was a circle right here. All right, so if this whole thing was a circle and this was the center of the circle, that would make this line right here the radius, right? Well, as the radius begins to travel counterclockwise this way around the circle, at some point this arc is going to become the exact same length as the radius of the circle. And when that happens, at that point, if you stop moving, then the measure of that angle is considered 1 radian. One of the things we cover in geometry when we do our chapter on circles is we learn that a central angle has the same measure as its intercepted arc, right? And so that's why if this arc is 1 radius or equal to 1 radius of the circle, well, then the central angle would also have a measure of 1 radius for the circle. So we call that radians, but remember, it all really comes back to its intercepted arc being the same length as the radius of the circle. And so when you do that, you get 1 radian. So obviously, as you keep moving, if you were to get to a point where you, say, double the length of the radius, so if from here all the way to here was 2a, so 2 times the radius, then you would have 2 radians, right? On and on and on as you continue around through the circle. So I just don't want you to lose sight of what a radian is, since we use those so much as we go through trig. So we do have a conversion ratio if you want to switch back and forth from radians to degrees and vice versa. So if we are going from radians to degrees, we simply multiply by 180 over pi. And just remember, all that comes back to is we're talking about length of a circle, right? We're thinking about circumference. If you were to travel the entire circumference of a circle, we know it's 2 pi r, right? And if the radius is 1, if it's 1 radian, so 2 pi takes you all the way around. So if you only went half the distance around, that would be 1 pi, which is the same thing as 180 degrees. And so that's where the conversion ratio comes in. Of course, if you wanted to go the other way, and if you were in degrees but you wanted to switch to radians, then we would take our degrees and we would multiply them by pi over 180. All right, and that would then put you back into radians. So for the arc length, and this is always done in radian measure. So as we look at this, a little formula that we get for the arc length, and that was like the A value that you were seeing up above, right? As we travel around the circle and the arc gets bigger and bigger and bigger, we're looking at the length of that arc as we travel around the circle. They use the letter S to represent the arc length. R is, of course, the radius, and theta would be the degree of the central angle that you'd be looking at. Keep in mind, when you're doing these formulas, they always do these in radian measure instead of degrees. So that's a formula we'll be working with. If you were given degrees for the problem. So if they give you an angle in degrees rather than radians, we will need to convert it to radians in order to get our answer, because again, they always do these in radian measure. So moving on. So one of the first things that this chapter starts out with is they start talking about this other way of writing degrees, which is in degrees, minutes, and seconds. Always kind of an interesting notation to me because it's really not something we use very much, but or at least kind of introduce it because it comes up in the book. So the reason they call this degrees, minutes, and seconds is it looks like this. So obviously you have your degrees here, and then the minutes and seconds have to do with the decimal following the degrees. So this becomes a portion of the degree, right? It's like less than one full degree. But it's called minutes and seconds because, as you'll see, it's a value out of 60 as we go through this. So you'll see how that works. So we're going to first start out with, if we were giving something in decimal form, how would you convert that to degrees, minutes, and seconds? Well, for the degrees part of it, that's always the whole number. So the 23 is our degrees. So we have 23 degrees, and then I need to convert the decimal into minutes and seconds. So really simple, actually. If I just take the decimal, 0.325, if I were to multiply that by 60, because here's the conversion rate, right? 60 minutes represents 1 degree. And that's why they call this minutes and seconds, because it's all based out of 60s. So here's the conversion ratio. If you multiply it by 60, it gives you this. So now what you're seeing is the 19. So the number that's now on the left of the decimal is your minutes. And I need to take the remaining portion, which is the 0.5, and convert him into seconds. So we take what's left of the decimal, multiply that by another 60, and now you get your seconds. So we had the degrees was 23, the minutes was the 19, and the seconds was the 30, right? And so they write that in this form right here. So they put the single little accent mark to represent the minutes, and then the double accent to represent the seconds. If you wanted to go back the other direction, so if you have an answer in degrees, minutes, and seconds, and you want to convert it back into sort of a normal decimal notation, again, we are going to look at the degrees portion of it as our degrees, right? That's the number that started out, as we saw in the last one, on the left side of the decimal. So 30 is our whole number. We know this was a value out of 60, right? If we're going back the other way, we're now just dividing by 60 instead of multiplying by 60. So I'm taking my minutes, dividing that by 60. And then the seconds, and here's what you got to remember on this one is, remember the seconds was another multiplier of 60, right? In order to get that, we had taken what we saw up here, and we had multiplied by 60 twice in order to get the seconds that we got. Well, if you multiply by 60 twice, that is a factor of 3,600. So when you are going back the other direction, we are now dividing by 3,600 in order to get back the full decimal. So again, we're just going to add up all the parts to this. So you got your degrees plus your minutes being converted back plus your seconds being converted back. And if we just add all that together, and this would all be a calculator thing, then you would get this. And you may even have this in a calculator feature of your calculator. I've seen calculators that have something like this, and it will like convert for you. So let's just do one for practice here so we can try one on our own. So we're given something in degrees. I want to convert that into degrees, minutes, and seconds. So again, we know the whole number on the left is our degrees, so that's 34 degrees. We're going to take the remaining portion of it, which was our 0.5, and we are going to multiply that by 60, and that is going to give us our minutes, which would be 30. And you'll notice at this point, I no longer have a decimal, and so I can stop here. There were no seconds to this one. So I was trying to give you a little different look than the example above so you could see what would happen. So it's okay to not have any seconds remaining. So on this one, our degrees was 34. Behind that, we have our minutes, which was 30, and they used the single accent mark to represent the minutes. And then if we had seconds, those would come next with the double accent. But this one didn't have any, so we could stop right there. So let's go back the other way with one. So in this case, we have our degrees, which was 10. That's our whole number, so he's going to stay our whole number. And to that, we are going to add the 30 minutes. And so remember, this is a factor of 30 out of 60, which is obviously 0.5. And then we also need to convert the seconds, which is 45. And this is the one you kind of have to remember. The factor on this was 3600 because it was a 60 times a 60 that got us this. All right, and so that's the way we would set it up, and I would just go throw that into the calculator. So let's say 10 plus 30 out of 60 plus 45 out of 3600. And now we have our answer back into regular decimal form. It would look like that. So about 10.5 degrees. All right, let's move on here. So for example 2, we're saying how many radians are in 45 degrees. So this is where we're just doing a little conversion on that. So we talked about going from, let me bump this down. So if we are going from degrees into radians, we know to multiply it by the conversion rate of pi over 180. Do keep in mind, sometimes people switch this up and they forget, should I put the 180 on top or the pi on top? The one you want on top is the one that you want to end with, right? Because as you learn, like probably already in science a couple years ago, when you're doing these conversion rates, these guys essentially cross cancel. So it's like the degrees cancel out and I'm left with whatever's on top, which is my radians. So whatever you want to end with should be on top. So if we're ending with radians like this one, I want the pi to be on top. So anyway, we just reduce that. Always reduce if you can. And that one ended in pi over 4. A couple other things. So if we were going to do pi over 10 radians, convert that to degrees, well, now we would just multiply by 180 over pi. And then we just simplify that. And obviously when you do that, the pi's cancel. And we'll look at that on the next page. The length of our intercepted arc. So this is 1/8 of a radian. And the radius was 24 inches. Real simple formula for that we saw on the first page of this document. And so we'll see that on the next page when I flip this over. And then the radian measure of a central angle. So still working with the same formula, but now it's like letters only instead of them actually giving you some real numbers. So let's talk about a few of these on this next page here. All right, so we already talked about doing the conversions. Super simple. You guys will have no trouble with that. So here's kind of the new formula that you may or may not have seen before, but if we look at arc length, this is the simple formula. They use S to represent the arc length. R is the radius, and this is our central angle. And remember, the central angle in this formula has to be in radians. So if they ever give you degrees for this, you want to convert it to radians first before applying it into this formula. So this one gave us the radius of 24. That's a simple plug-in. They gave us the central angle, which is the 1/8, and then we just simplify. So that would be the length of our arc. For the last one, what they were trying to get you to see on this guy, let me just lay it out real quick. So here's our radius. So they wanted you to see how you could rework this formula to isolate the angle. So I know this is my arc length, I know this is my radius and my central angle. What if we were trying to find the central angle? Well, if I divide the r over, so if you take your arc length, divide it by the radius of the circle, that would give you the measure of your central angle in radians, of course. Right? And so there's a relationship here that we're going to see a ton as we get more and more into the trig stuff and unit circle and all that good stuff. Obviously, if our radius is 1, which is what the unit circle is, that's why they call it the unit circle, right? Because the radius is 1. Then all of these things simplify. We see that if the radius is 1, that the arc length would also be the same as our central angle, right? And we already kind of talked about that. So We'll do a couple practice problems here. If you want to pause, give these a try, always a good thing to do. So let's do a little conversion into radians. So if we multiply by pi over 180, then we would get our answer in radians. Always want to reduce those as much as you can. So if we reduce our 72 over 180, this guy works all the way down to 2 pi over 5. If we're going the other way, we're taking our pi over 6, multiplying by 180 over pi. And again, you can see that the pi's would cancel out. So it just becomes 180 divided by 6, which we know is 30 degrees. And as far as working with the new formula, so we got S equals R theta. We know the central angle is 1/3 radian, so that's going in for theta. We know the radius was 42, so just a straight shot into that formula. So that was our radius, 1/3 for the angle. Just simplify that, we get 14. So a real simple formula for that one. Let's jump on down to this guy. So I'm just going to have you fill this one in with me, save you some writing. So over here we're looking at our slice of pizza, so representing a portion of a circle. We call this a sector, right? A sector of a circle. So you can see that the radius is 10. Because one thing to keep in mind is sometimes they won't give you the value for both of these. Remember, a radius never changes, so if they just gave us one of these as being 10, automatically we would know the other one is 10 as well, right? Because they're both represent radii of the circle, and they have to be equal. So this one's saying they'll find the perimeter, 45 degree slice of pizza, 10 inches in radius. So on this one, it's really similar to what we just did up here. It's just making sure that we add up all the parts to get the perimeter. So if we look at the perimeter, we're looking at our 2 radii plus whatever S is, right? So we're going to be adding up all 3 of those lengths in order to get the perimeter. So we just have to solve for S so that we can get the perimeter on that. So if we did our formula, notice on this one they did give us a 45 degree angle, so be careful on that. We are going to have to convert that into radians in order to do this. So let me do this. I'm going to put the radius as 10. And then I do have a 45 degree angle, but we're going to need to convert that in order to get our answer. So we'll kind of lay out the whole thing this way. So this is what the setup would look like in finding S. So we got 450 divided by 180, so 45 over 18, which would be 5 pi over 2. So that would be our S value. So now we can just add up all the parts. So obviously 10 plus 10 is 20, 20 plus 5 pi over 2. So if we wanted to leave it in exact form, we would just write it as 20 plus 5 pi over 2. Oops. Plus 5 pi over 2. So, but if we did want like a decimal answer on this, we're looking at about 27.9. All right, moving on to example 3. So we're going to take a look at something out of your book real quick before we get into this example. Let me switch over to page 316. So here's a little something on page 316 that talks about the difference between angular and linear speed. Kind of interesting. If you actually look at your dashboard on your car, you'll see. Obviously, you're very familiar with your speedometer, right? To tell you how fast you're going, that is your linear speed, right? Those things get measured in things like miles per hour. So all this has to do with simply how fast you are traveling in a straight line, right? And we talk about the distance that you would travel horizontally over a period of time. So we're all familiar with miles per hour and linear speed, but also a dial on your dashboard is also going to say RPMs. And so you can see how fast you are going in revolutions per minute. That is your angular speed. So the angular speed, so kind of think of this as a tire right here. So angular speed has to do with your tire, how many times it is rotating per minute. So when you say RPMs, you're saying how many times my tire completes one full revolution every minute. So if you were to look at the dial on your dashboard that says RPMs, and if it were to say 630 RPMs, then what we're saying is my tire is rotating 630 times every minute, right? And so because it obviously depends on the diameter of your tire is going to affect that, but it's telling you how many times your angular speed, because now we're taking into account this direction, how many times that's happening every minute or in some given period of time. What we're looking at on this one is simply converting from angular speed to linear speed. So if you were to look at the dial on your car and it were to say this, what does that mean in terms of mile per hour, right? So if we go through these conversion factors and convert it all into miles per hour, so this is what your speedometer should say if this is what the other dial says on your car that measures the RPMs, right? And so what we should see those things kind of match up if we do this right. So let me take you back to the one that we're looking at on here. So on this one, they were telling us that the angular speed was 720 revolutions per minute, and we wanted to convert that into a linear speed of miles per hour. So one thing you would need to know for this is what is the radius of our tire that we're working with here. As we just looked at the connection between the angle, the measure of the central angle, and the radius of the circle. So if they give us something in terms of a diameter, of course we could divide that by 2 to get the radius. So we're working with a radius of 18. So, and they're just going through a series of conversions that you guys have seen before. So for example, if I had 720 revolutions per minute, if I'm trying to get this into miles per hour, one of the conversions that we would need to do is convert from minutes to hours. So that's what you saw right here. And then the rest of this is all about converting the 720 revolutions into miles. So do keep in mind that one revolution, one lap around the circle, would be one circumference, right? So when they say 720 revolutions, they're saying 720 circumferences. So if we want to get the revolutions into a length like miles, we need to start thinking in terms of length. So we don't want this in like a degrees. We would want to see circumference in terms of radians. And as we just saw up above, our arc length, right, is done in terms of radians. And so we know one full lap around the circle would be 2 pi. So we're starting out by taking these revolutions, and we're going to throw in the conversion factor here in order to put these in terms of a length in radians. So as we saw right here with a diameter of 36, we know that's a radius of 18. So they're going to take, now that it's been converted into radians, they're going to say, well, we know that 1 radian is 18 inches, because that's the radius, right? So that's 1 radian is 18 inches, the radius. So now we're converting from radians into inches, and then from there, now we're kind of hopefully back into some familiar territory. We are now going from inches converting into miles, right? And so this is the way it all laid out as that was done. Just remember some good old science stuff that you would have seen as early as probably junior high. As you were doing these conversion factors, we always put units opposite of each other so that they'll cancel as we go into the next unit. So like if I had inches on top, over here I want inches on bottom so that my inches cancel, and now I'm in feet, right? And over here I want my feet to cancel, now I'm in miles. So just keep that in mind. Let me flip over so that we can try one of those. Always okay to pause and give this one a shot. So we know 40 inches in diameter, so of course right off the bat let's start thinking 20 inches is the radius. So let's start setting up our conversion here. So we're starting out with 600 RPM, so that's revolutions per minute. So we have our 600 revolutions per 1 minute. And again, if I'm trying to get to miles per hour, and these can go in any order because of multiplication, right? We know I can switch the order. So you could do this in a different order and still come up with the same answer. But if I want to get at least from minutes into hours, let's throw that one in. So we want our minutes to cancel so that we can end up in hours. So let's throw in our conversion ratio for that one. And from there, we now need to get our revolutions into terms of a mile, right? So we're thinking length on this. Remember, 1 revolution is 1 circumference. So let's first get this in terms of length. We know 1 lap around the circle would be 2 pi. So we know that 1 revolution would equal 2 pi radians. So now we are getting into terms of length in radians. We know that 2 pi radians would equal 1 radius of the circle. So remember, that goes back to this drawing right here, right? So if we're in terms of radians, so 1 radius should equal my arc length on this guy, right? So there's our conversion factor right there. So we need our radians to cancel out. So 1 radian would be 1 radius of the circle, which we saw up here was 20. So now we, in terms of inches, just need to get that into miles. So we're going to go from inches to feet. So 12 inches in a foot. 5,280 feet in a mile. And now we would be in terms of miles. So as we basically multiply straight across and then reduce, we are then going to have our answer in terms of miles per hour with all those conversions. So you can simplify that, just multiply it through. Let me do one last problem with you. So we're going to look a little bit at bearings of travel here. So compass bearings are measured clockwise from the north. So here's kind of what's important about that. So if you think of like your basic directions here, so I'm looking at north, south, east, and west. So when they give you just a general bearing, if there's nothing else said about it, if they just say it's 35 degrees, 80 degrees, whatever, then that is your degrees clockwise from the north, so you would be going this direction, right? So they would be describing this angle right there, right? So just keep that in mind. Let's set this one up. So ship travels 4 miles at 35 degrees, so we'll start sketching that. So we know that the angle from the north, so if I were to go about 35 degrees that way, would put me about here. All right, that's our 35 degrees. So here's our ship, and it's going to travel 4 miles along that angle. So we know this is our 35 degrees, and this is a length of 4 miles. So that's what they've given us so far, and from there it's going to change course. So right now he's here, right? But he's going to change course, and now he's going to go 80 degrees from the north for the next 8 miles. I definitely should have drawn this sketch a little lower, but that's okay. But here's what we're seeing. So now he, from here, if I want to figure out 80 degrees, so this is his new spot. And so if I need to go 80 degrees from the north, so what that would be about here. So his new path is going to look like this. And they're telling us that was a distance of 8 miles at 80 degrees. And so that's as far as this one is going to go for now. I just wanted you guys to start getting used to the bearings of what they look like, how the degrees work, and how we would make a sketch. Down the road, of course, we can turn this now into a triangle. Like they might say something like, so how far is he from where he started? So if I were to look at this length right here, now I'm looking at a triangle, and now we can throw in some trig and things like that. So, but this one was just to get used to the sketch and making the drawing. We'll be working with those more down the road.